Okay, so we're looking at dynamics, so displacement, velocity, acceleration. We've done this before, but we're doing it with we're just sort of upping the ante a little bit here. The important thing to note is that this motion may not be in a straight line. So last time we did dynamics, displacement, velocity, acceleration, everything moved in a straight line in one dimension. So we would take something from a cliff and drop it down, it would fall straight down. Or there was a sprinter and he'd run in a straight line. But if you fire a cannonball, it flies through the air in a parabolic arc. So it's moving upwards, but it's also moving acrosswards. It's not like a sprinter that just goes straight along the ground. It's moving in more than one dimension. So it's going to be useful to use vectors in terms of our displacement, velocity, and acceleration. So that's where we're headed. That's why we're going to be using vectors for this next year. Free to copy down the rest of this stuff, and I am going to talk pretty much like about this, but instead of using all this fancy notation, we're just going to look at it on GeoGebra and try to get a feel for what it really means. Here we are. Now, point B is going to be our particle, and our particle is moving through two dimensions, so through an I and a J component. So it might be a cannonball or whatever, so it's moving acrosswards, but it's also moving up and down. And we can show that with our I and our J components here. Now this is our I axis here, and this is our J axis up here. Now, note how I've written my vector. 8 minus ti, so t is our time variable, plus 8 minus 4t plus t squared, j. So that means that as time progresses, our I and our j components are going to change. So when time is equal to 0, our particle starts at 8, 8, 8, 8. The t components don't do anything. But as we move to, say, t equals 1, you can see the particles moving sort of down and back closer towards the origin. And now we're at 0.73. In fact, sorry, 7.5. There we go. Okay. So there's just, it's the same formula. It's just calculated for you. When t equals 1, I is 7 and j is 5. And we can see as time moves forward, our particle shifts downwards, 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 and then it's starting to move upwards and takes off into space here. And our I component becomes negative, and our j component's really sort of taken off into space there. Okay, so sort of do that back a couple of times. It's sort of like a parabola going on there, and that parabolic shape is being created by this component here. And obviously we can create more and more complicated movement patterns by changing our I and our j components there and there. So that's what we're going to be working with. We're going to be working with I and j components, which are x and y axis, and we're going to be working with a time component that changes both of those simultaneously. Now that idea does appear in these notes where it says, if we write RT to represent, then we may say that this, some function of ti plus some function of tj, different functions of t, but a function of ti plus a function of tj. That's what, going backwards, that's what this is here, a function of ti plus a function of tj. Of course, sometimes it's useful to know the I component, sometimes it's useful to know the j component, but sometimes it's useful to know the absolute magnitude of that vector. If this is our origin, sometimes it's just useful to know how far something is from the origin, and you can do that just by finding the magnitude. R equals the magnitude of RT. Now you can feel free to copy down these notes here, but all this says is, okay, if this is a displacement vector, then we should be able to find the derivative of that to tell us the velocity vector, and we should be able to go one step further and find the derivative of that and find the acceleration vector. So we should be able to find displacement, which is what this is. Velocity is the derivative, and acceleration is the derivative of that. But you've all done that stuff before. One interesting thing that you've never used really before is this little R dot above to denote time derivatives. So this is the derivative of RT, and this is the second derivative, 2 dots for acceleration. Okay, that's what we're working on. Let's just jump in and try a couple of questions.